Hello everyone, this is Michael from Battery Hacker. In this video, we're going to answer a very common and important question. How many batteries do you actually need to run a 2000-watt inverter? Many people buy an inverter first and then get confused about battery size, battery quantity, and system voltage. That confusion usually leads to poor performance, short battery life, and wasted money. Today, we will simplify this step by step. We will focus mainly on a 2000-watt inverter, and we will look at battery sizing using clear calculations that anyone can understand. We will also compare lithium batteries and lead-acid batteries because both behave very differently when used with high-power inverters. Before calculating battery capacity, we must first understand system voltage. A 2000-watt inverter can be found in 12-volt and 24-volt versions. But for this power level, a 24-volt system is strongly recommended. Here is why. When you run high power on a 12-volt system, the current becomes very high. High current means thicker cables, bigger fuses, larger circuit breakers, and more energy loss in the wiring. All of this increases cost and reduces efficiency. By increasing the system voltage to 24 volts, the current is reduced. Lower current means smaller cable sizes, less heat, lower losses, a more efficient and safer setup overall. That is why, for a continuous 2000-watt load, a 24-volt inverter with a 24-volt battery bank makes much more sense. Now that we understand why system voltage matters, in the next part we will start the actual math and calculate how much current a 2000-watt inverter pulls from a 24-volt battery system. Now let us start with the actual calculation. We already know the inverter size is 2000 watts, and we are using a 24-volt system. To find out how much current the inverter will draw from the batteries, we divide power by voltage. 2000 watts divided by 24 volts gives us 83.3 amperes. This means that when the inverter is running at full load, it will pull 83.3 amperes from the battery bank every hour. So, if you want to run the inverter for 1 hour, you need at least 83.3 ampere hours at 24 volts. Now let us extend this to longer runtime. If you want the inverter to run for 5 hours, you simply multiply 83.3 ampere hours by 5 hours. That gives us 416.7 ampere hours at 24 volts. So, before considering battery type, depth of discharge, or battery chemistry, this is the raw energy requirement. 1 hour of runtime needs about 83.3 ampere hours. 5 hours of runtime needs about 416.78 ampere hours. However, batteries cannot be used at 100% capacity safely, especially if you want long battery life. That is where depth of discharge, also called DOD, becomes very important. Let us now factor in depth of discharge. If you are using lithium batteries, you can safely use around 90% of the battery's total capacity. That means you do not need to oversize the battery bank too much. For lithium batteries, when we adjust for depth of discharge, the requirement for 1 hour of runtime becomes approximately 92.6 ampere hours at 24 volts. This can be rounded to a 24-volt, 100 ampere hour lithium battery for 1 hour of runtime. For 5 hours of runtime, the adjusted requirement becomes approximately 463 ampere hours, which can be rounded to 500 ampere hours at 24 volts. That means 1 hour runtime, 124-volt, 100 ampere hour lithium battery, 5 hours runtime, about 500 ampere hours total capacity. Depending on battery size, 250 ampere hour batteries, you need 2. 200 ampere hour batteries, you need 3. 100 ampere hour batteries, you need 5. Now let us look at lead-acid batteries. Lead-acid batteries should only be discharged to about 50% if you want reasonable battery life. After adjusting for depth of discharge, 1 hour of runtime requires about 166 ampere hours, which can be rounded to 180 ampere hours. 5 hours of runtime requires about 883 ampere hours, which can be rounded to 900 ampere hours. This means lead-acid systems require many more batteries compared to lithium for the same inverter and runtime. Now there is one more very important factor many people ignore, and that is C-rate. For long battery life, lithium batteries perform best when charged and discharged at around 0.2 C, which is 20% of battery capacity. For example, a 100 ampere-hour lithium battery has a recommended continuous charge and discharge rate of 20 amperes. Running a 2000-watt inverter from a single 100 ampere-hour battery forces the battery to operate close to 1 C, which increases heat and speeds up battery degradation. To stay near the recommended 0.2 C rate, a battery bank of around 500 ampere hours is a much healthier choice for a 2000-watt inverter. The key takeaway is simple. Always size your battery bank not just for power, but also for runtime, depth of discharge, and long-term battery health. If you plan carefully, your inverter system will be more efficient, safer, and your batteries will last much longer.